Previously on electric fields, we looked at all kinds of drawing things, okay? We looked at, how do you draw if your charge is around positive charge? You get it radially coming out. Make sure wherever you leave the surface, that part is perpendicular. Then if it's negative charge, it's all going in. If they're side by side, they kind of do a nice connection. They fall in love, they connect. I try to draw it smoothly. There we go. That's a bad one. Anyway, the fields still have to come up perpendicular to the surface, but what they do after that, I don't care. Oh, by the way, if you have seen the word dipole, it means dipole. Basically, it means two charges that have pretty much gotten married and become one molecule. They call it a dipole. That just means one molecule that has two ends, which is positive, negative charge, and yeah, that's what it means. And we also looked at charge and plates. If you have a charge in the plate, how does it look like, and all those kinds of fun stuff. But we will be focusing more in AS for a certain type of electric field. What happens in a certain electric field, and that will be electric field for parallel plates. That's what it means here, parallel plates. So we're only going to zoom in a lot on electric fields that look like this, uniform, space, same electric field strength, and this is what we're looking at today. How do you find that field strength E? E here means field strength, not energy, and not, there's another E. Young's modulus, no. Different chapter, different E. How do you find the field strength? And how do you find the force on a charge inside there? It's kind of a recap of last week as well. If you have a charge in there, where is the force acting on it? Will charge fly there or fly here? So let's take a look at the uniform field. Uniform field, okay, you can only create this uniform field if you have two parallel plates connected to some power supply. If not, where they get the voltage from, okay? So it's kind of like your phone and your calculator, just put side by side like that. Okay, can't do a 3D rotation. Okay, so that's your parallel plates. Remember, they're plates, so we're only looking at the side view, which is kind of making them like two lines. Okay. All right. So how do we get the potential difference again? How do we make a electric field? Well, nothing's connected. If you just put two plates, no electric field. But if you connect a power supply down here, let's say I put some potential difference V. This V is like voltage. So let's say I put a power supply that kind of spits out 100 volts. Wow, very big battery. Plug there, connect the two plates. Oh, then both sides will get pretty charged up. Let me use red color for here to signify electricity. So you get charged up, and let's say this is the positive side and this is the negative side. So send electricity down the wire, go up. On this side, you're going to have the positive plate. So I will say, well, positive. And in the other side, it's going to be of lower potential difference. So I call it a negative plate. So negative. Okay, so on this side, you have 100 volts, and this side, the other side, probably just 0. Okay, potential difference. We'll learn more on that in the future chapter. Okay, so now we got voltage. What about the field? Remember, the field, the arrows basically tell you where would a positive charge move. Think about this. You put a little positive charge inside there. Where will it fly? To the left or to the right? Opposites attract. So you want to go to the right. So all your arrows will want to go to the right as well. So you have something like this. And they're not arrows here, so let me add arrows. Some key characteristics to remember. These equally spaced field lines means that throughout everywhere in the field, the electric field strength is the same. Let me make a note here. E field, same. Well, E field strength, I should say, is same everywhere. This is only for parallel plate uniform electric field. There's actually a formula for it, but hang on a second. Okay, so we got the field, we got the potential difference. Now all we need to do is put in some test charges. Let's see. Do you remember what was the equation for force from the previous video? How does force and electric field relate? Remember, one way of measuring how strong electric field is, if you put a charge inside, what's the force that you experience, right? So something related to force and electric field. That is F equals to QE. This is one of the main equations you will want to remember throughout the chapter as well. So this Q here basically means if you put a, what shall I use? If you put a positive charge, where is it going to go? It does not like positive. You want to go to the opposite attract. So this little charge is going to experience a electric force this way. This is called FE, like electric force. And that force is the same everywhere throughout the field. Okay? Same, if you put another one here in the middle, further down, still the same FE. Why? Because electric field strength is the same everywhere. What if you put, okay, let me say this F is positive QE. Big Q is just some charge in coulombs, C for coulombs. What if you put an electron now? Let me use red, not use red. Let me use green, electron. So you put an electron here. The electron will want to go to the positive. So your force that you experience will be actually in the opposite direction. So FE this way. If you want to write it out, force will be some negative charge times the electric field strength. So yeah, that's where the negative sign will come into play. But basically, we don't need to worry too much about positive, negative, just know which direction it is. Notice how the direction of this force is reversed to the direction of this field because it's an electron. Okay, electron. So remember, the convention of where all the field line point is focused on the positive proton only. So these are electron, proton. Okay, so that's the main idea. We'll be focusing a lot on this. Last thing, remember I mentioned there's an equation for electric field, right? Oh yeah. You see the right side there already got F equals QE. There's actually another one. This is how you can change this electric field. What do you think changes the electric field strength? Could you change the voltage V down there? Make it like 240 volts? How would it change? There's a way to change it. If you put the two plates closer or further, will the electric field strength change? Actually, it's yes. They will change, and here's the equation which basically summarizes their relationship. So the electric field strength here depends on two things. The potential difference between both plates, the V, the big V, divided by the separation of both plates. So that's what we call D. Oftentimes you see people write. So V is there, D is this thing, the difference between here and here. How many cm, how many meter, how far apart? Okay, so this is the main idea, the foundational concept of the entire chapter, uniform electric fields, charges flying around. The future videos from here will be a lot of application and things like that. But before applications, let's learn more about this uniform electric field. So remember I mentioned they vary, right? But how exactly does electric field strength vary? Depends on two things, like we said, potential difference and plate separation. E equals to V and D. You need to know this because they will ask you to show graphs. How do you plot graphs about E versus V or E versus D? So you need to know how you can think of the relationship. Okay, let's say we have 100 volts on this side, 0 volts on the other side. So left side is more higher potential, so we'll call that positive side, and then the negative side. Okay, so that's correct. We have that field strength. What if I switch up the voltage a bit? What if I up the voltage and I say, here is 200 volts and here is 0? Wow, very power. Well, now you have a potential difference of 200 already. So the field strength should be much bigger, 2 times bigger in fact. So to symbolize that, I'm going to draw double the amount of field lines inside here. There we go. Okay, how do I know that? Because firstly, E is V over D. V means potential difference. Okay, 100 minus 0. If your V increase, means, where is my arrow? Means your E will also increase. V increased 2 times means your E increased 2 times. That's what the ratio thing means. Okay. Oh, also, if I change this to 100 volts, and then this one I put negative 100 volts. Wow. Same, still the same, because here the potential difference is actually 200, because 100 minus 100. If you want to think of it that way, then it's 200 volts. So remember, our difference is left plate, right plate. What's the difference between both? Okay, that's one thing. Potential difference and plate separation. And if you want to plot out their relationship, here's how it looks like on the on the right side. So if you have E against potential difference of the plates, got potential difference, got electric field strength. So proportional. Ah yeah, straight line lah, straight line. So E is proportional to V based on this equation. Imagine it's a straight line, not as pretty. Anyway, the other thing we can change is, what else can we change? Oh, plate separation, right? So we start off with good old plate separation. Maybe this is 100, 0. And then I make them smaller. Zoop, probably almost half the distance. So up here I have some distance D. Now it is half the distance D. Do you think the electric field strength will be stronger or weaker? Here's how we can think of it. You look at the equation here. E equals V over D. If D gets smaller, it's down there in the denominator, so you divide by a smaller number. Means E will get bigger. Because if I do here, half the distance, that is basically saying 2 times of E. Because, 1 over half and then E. So I should get a relationship something like this. Inverse relationship. E is proportional to 1 over D. Where this come from? I'll look at the equation. E on top, D at the bottom. So if I plot a graph of E against separation of the plates, D, it's going to be an inverse square law, which looks something like that. You just need to remember roughly what it means. Proportional means straight line going up. Inverse law means 1 over something, is that curvy thing. So I should also draw, to symbolize double the field strength, means I draw more arrows there. More arrow means stronger field strength, no? Okay. So, okay. So that's the main idea of what's happening here if you vary field strengths. There's a very quick simulation I want to show you. If you're like, I'm not convinced of this, go try it out. So the next part, we're going to have a quick pick at the simulation in GeoGebra. So here's a very nice, fancy way of checking out electric field strength. Very handy. First, you can check out electric field lines and see, okay, everything's pointing down. Then, not only that, this person has given you a great shortcut. You show how to calculate the electric field strength inside there. Okay, first thing, remember I mentioned electric field strength is the same everywhere. Well, let's check that and see. Here I got an E field sensor on the left, so I'm going to enable that. And I can check everywhere. It's 10 volts per meter, like what we calculated down here. Okay, so electric field strength is the same everywhere you go. First thing, remember, that also means the force acting on a particle will be the same everywhere inside this electric field. Okay, so I don't need another sensors. What I want to play with now is these two things. The voltage between both lines and also the plate separation. So are they narrow? Are they very far? Okay, so first things first. Let's play with the voltage. Like we mentioned earlier, higher voltage, more field lines. Let's check it out. So if you increase the voltage, you see more and more field lines appear. They're also closer to each other, and you see electric field strength doubles. Okay, let's go back to 50. If my voltage times 2, this electric field strength should also times 2 and become 20. So if I change this to 100, this should go from 10 to 20. That's right, because 100 divided by 5. Now, let's plot out the points. You will see that if you start at 1, 1 is really, really small. So if you plot E against V, on the right side here, you start off with near 1 volt, you have a very tiny 0.2 volts. If you go to 10, you can check out we got 2 volts. If you go on to 30, you got 6 volts, 40, 8, 50, 10, 60, 12, so on and so forth, 14, 80, okay, all the way to 100, which is an electric field strength of 20. There may be experiments that will ask you to do that, you know, measure voltage, measure electric field lines, but those are not lab style because we don't have a tool to exactly measure electric field lines directly. Okay? We can do the same thing for electric field lines to double check what actually happens. So we start off with a very small separation. Wow, that's a big 50 volts per meter electric field strength because they're very close, you know. Basically, if you and let's say somebody you really like, romantically like, are very close together, wow, then a lot of field strength, a lot of what we call a lot of chemistry happening because they're very close to each other. Okay, anyway, so you start off with 1 meter separation, you get 50 volts. Or if you go to 2 meter separation, 25, wow, half already. Then if you go to 3 meter separation, then your field strength drop until about 16, 17, go some more until 4 meters, 12.5, a bit slow in decreasing already. Go to 5 meter separation, down to 10. So then if you plot out all these points and fit a nice curve through it, you get what we saw earlier called the inverse law, where you have E is proportional to 1 over D. So go play out more with these simulations if you're unsure of how to think about how does voltage separation and electric field lines come together. Go check it out. Play with it. The link is down in the description below. Before we go any further on electric fields and voltage and all that stuff, let's try out a question on calculating the electric field by yourself. No help of those fancy simulations. This is on page 16 if you have the handout. I want to try it out as well. So we have a particle in the vertical electric field. Electric force acts on the particle. What is the electric field strength? That's what we're trying to find. So pause the video, take a pen, doodle on some paper, really quickly come back and check if we got this right. This is the basic one. You should try your best to understand and comprehend the question. Okay, if you find this confusing and hard to imagine what's going on, the first thing I suggest you to do is, may I suggest you something? Draw out the electric field. Physics question must draw one. Okay. So you practice drawing, check if you got this correct. So you want to have, well, 2 parallel plates. How we know it's uniform electric field? Oh, they told us. Okay. Uniform. Very good. No need to worry about weird stuff. So 2 parallel plates, uniform electric field. Which direction it is? Don't know yet. I'll just draw lines first. There we go. And now you have a particle inside there. So particle, positive or negative? How do you know? Well, this is a hint. It's telling you the charge, Q. So it's a positive charge. And it has the charge of, well, let me just write down. Q is, in this case, 2, what is MC? Microcoulomb. So microcoulomb. Coulomb is the unit for charge. What else do we know? Electric force. Oh, very important. Okay. So electric force acts upwards. Fe. And we have that given to us. Okay, good. What is the electric field strength? Okay, so you see you got F, Q, and they're asking you what is E. You must remember, formula F equals to QE. So you plug in everything you know. What is F? 1 times 10 negative 2 newtons. Make sure it's in newtons. Charge of this positive thing. I call it a proton or whatever charge. There's so many things as positive charge. Q will be 2 microcoulombs. And lastly, E. What is E? We don't know. We're trying to find that. So all you need to do is rearrange the equation so we can find E. And you should get about 5 what? 5 what's the unit? Well, if you try to divide, if you say it's Newton per Coulomb, can also. That's one way to say it. So you can say it's Newton colon -1, or you can say it is 5 volts per meter -1 also can. Why are there 2 units? Because there's 2 equations. You have F equals to QE. or rearrange E equals to F over Q. You also have E equals to V over D. So many formula, many unit lor. Okay, so here will be 5 volts per meter. You look at the answer on the top right. 5 volts per meter, is it up or down? How we know? You must think very carefully. Look at the left side picture that you draw or I draw. This positive thing is going up. Means the electric field lines will also be going up because in the first place, these lines is the direction a positive charge will go. Okay, so if field lines point up, positive charge move up. Okay, that is if the positive one, if electron is different. So in the sense, here will be positive, here is negative side lah. Okay, all right, so here we will say it is upwards. So 5 volts per meter D. Direction matters, okay? Because force is a vector. Electric field is also a vector, as you can see here, upwards, downwards, left or right. But in our calculations, we usually just take the magnitude. The vector part, we save it for A2. Okay, so that's the short and sweet starting for calculating electric field strength. This next one looks like a bomb. So many information. Wow, where to start looking? It's on page 13 if you want to try it out as well. So yes, this one is not as complicated as it seems. So try it out first. Try to interpret it. Use some exam skills and see how to deal with this thing. Okay, 2 parallel plates, 4 meters apart, X, Y, Z, 3 points. Okay, X, Y, Z, Z, Y, X. What is the electric field strength at X, Y, and Z? Wow. So we just have to calculate one by one. Some people will ask, do we have to calculate the electric field strength at X, Y, and Z? Maybe, maybe not. Well, remember I mentioned if you are in a parallel plates, uniform electric field. Uniform means everywhere inside this whole thing. Wow, my line very pretty. Become straight line. Everywhere inside the field line, the electric field strength is the same. So X, Y, Z should have the same value, whatever that is. I don't know. I can just look at the answer straight away and see, that means A and B is out already. C and D possibly, because C all 3 same, D all 3 same. But how do we know which one is it? So we need to calculate the electric field strength. We can't use F equals QE because they didn't give us force. Okay, so we will use this one, V over D. The question is, well, I know V. I can find V, but how do I find V? Which one to use? V, I know can be, find the difference. So you have 2000 minus 800 volts. What's the difference between both of them? Usually I just take the higher one minus the lower one. How notion is the one? Well, what do I use for D? Do I use 4 cm, 3 cm, 2 cm, 1 cm? Well, this thing is a separation between the plates. So you want to take the full plate, so it's 4 cm. But don't just write 4 cm. You need to convert to meters. So 4 times 10, negative 2 meters. I should write the top ones also volts. Okay, now we can calculate everything. So 2000 minus 800, 4 times 10 is negative 2. That is 3 times 10 to the 4. What shall I use? Volts per meter and coulomb? Let's use volts per meter here. Since we already use voltage per meters. So here the answer will be C, not D. Now all this cancelling of A and B is to help you save time a little bit. Make sure you don't accidentally choose A or B. Okay, so not these two because E is the same. Let me just make notes. E same at all these positions. E field strength lah. I should write E field strength. Okay, so that's how you can solve problems related to trick problems related to this. They may say calculate the different field strength. Actually, not to calculate, they're all the same. Electric field strength is the same everywhere in a uniform electric field. Okay, this equation can only use for uniform electric field, means straight line like that. Okay. Previously, we did a bunch of questions on electric field. Now we're going to focus more on 3 questions, 2 normal ones, 1 kind of a challenge question. 3 questions before I wrap up the video on the force acting on the particle, the electric force. So here we start out with something more fundamental. Diagram shows the electron in a uniform electric field. In which direction will the field accelerate the electron? This is on page 11 for if you have the handout, you want to try it. Okay. Page 11, this one, no calculation involved. You just have to look at the picture and try to interpret what's going on. Okay. So, why suddenly got acceleration one? Huh? Well. Remember, we have electric force. Okay. So, force acting on the electron because of electric field. But this force can also relate, throwback to Newton's law, F equals to ma. Got force means got acceleration. Oh, I shouldn't put that. Okay. Got force, got acceleration. So that's where the accelerate, they're basically asking you in which direction is the force pointing. So you need to look carefully and see, okay, arrow is pointing this way, the electric field arrows, means that is where a positive charge would go. Okay, or you're going to think of it this way. This is the higher potential, this is the lower potential. Okay. So if you want to say, oh, if you put an electron inside here, you want it to go to the opposite, so it will go to the left. So that is where you can say, okay, this is where the electron will start to accelerate because there is a electric force acting on it. Now remember I mentioned if I change the question a bit, if I say, now this one is a proton. Where would it go? Go in the opposite direction here because these arrows show where a positive charge will go. Proton means positive charge lah. So remember, positive charge follow the field lines. Negative charges like electrons will go against that. Means reverse law. Also because they are attracted to the higher potential side. Alright, so that's the basics. Make sure you don't confuse this one up. Look very carefully. There are some trick questions that will come along and troll you if you don't look carefully. When they say electron, electron means negative charge. So you want to think accordingly. Now, let's actually calculate the force of the electron. Pause this one out. See if you can figure out how to do some gymnastics and find the electric force of the electron. Just a warning, it's not exactly straightforward. You might have to plug in some other information and equation. This is on page 16, by the way, if you have the handout and want to try it out. If not, just go online, find a pass here, or just take a paper. Just look at the screen and try it, huh? Okay, pause the video, try it out, and we'll go through it together. Okay, first things first. You see they want force. Wow, got distance D, got potential difference. Actually, people should write delta V lah. Means difference in voltage, but as long as you know the V in the equation means potential difference. Okay, so the master equation you want to remember firstly is F equals to QE. If you got that down, good. That's the first step. You want to find F, electric force. Do we know Q? What's the charge of the electron? Well, it's not given to us here, but it's one of those universal constants which you should know, memorize, or have the formula sheet to refer to. So there's an exam formula sheet where things like gravitational constant 9.81 are written there. It's something you want to write down, or some of your calculators may have the calculator cover that write all the constant there. You want to look for the one that says E, charge of the electron. Or you can just press shift constant 23. I memorize it because exam they say cannot bring calculator lead. I just memorize all the constants, so I plug in. Okay, that's a trick you can do, exam hacks. So we do know the charge of the electron, QE, or sometimes in your calculator may write it as E. That is 1.6, technically negative 1.6 times 10 to the negative 19 coulombs. There we go. So we do know that information. How about E? Do we know E? We don't exactly know it, but we can plug in the equation that we know earlier. E is voltage between plates, potential difference between the plates, and how far are they apart. So let's plug that in. So we have V over D. That gives us the equation QV over D. Hey, now we can calculate. So let's calculate the force. So what we have, 1.6, I'm going to ignore the negative for now because I only want to know the magnitude. The direction, I don't need to know yet. So 1.6 times 10 negative 19 times potential difference. You have to be very careful with this one because one is a positive, one's a negative. So let's take the bigger one, or the more positive potential, minus the lower potential, which is like very, very low, 500. Minus 500. Divide by the difference, which is 5 times 10 to the negative 2. Why negative 2? Because I want it in meters. Yeah, meters, and this one in volts. Now we can calculate it. Okay, constant, charge of electron, 2000 minus 500, divided by 5 times 10 negative 2. Ooh, that is a very, very small force. That's like 8.01 times 10 to the negative 15. Wow, very small. Usually we talk about, body weight, car flying, how many thousand newtons? Tiny little. Anyway, so here you look at the answers on the top right, the one which will suit it is D. That is the answer, and that is correct if you got that. Things to be careful of before we move on to the last one. Positive, negative. You want to think of it as higher potential, lower potential. Okay, so if you have, this is the higher potential, lower potential. You can think of it as the positive and the negative plate. So you would draw stuff like this. Electric field lines kind of thing. Higher to lower. In the next video, we'll look a little bit more about what potentials really mean in electric fields. We'll save that for the next video, potential and work done. But yes, be careful of that because this part will come into play. Wow, I should use red color. And remember that both equations, this and this, both work together a lot. So you just need to know, list out your information. What do you have? What are you trying to find? Kind of like what we do with Stuva equations and things like that. Okay, now the final challenge question. This is called a dipole. Dipole means two charged opposite, they get married, they become a molecule tied together, and it's this gray color blob we call a dipole, if you ever see that word. This is from some years back. This is structured from page 17 of the handout. 17. And here they ask a very interesting question. The molecule is sitting in the electric field at the angle, so this angle here. It's not exactly aligned with the electric field. Calculate the torque on the molecule because of electric forces. Torque. Where got torque come from? We have seen torque before in the previous chapter. Which chapter was it? Torque chapter 5. Forces and torques. Wow. So how do you find the electric force? Try and brainstorm on this one. And I would say, if possible, try not to give in and watch the answer straight away. Try to just figure out how to wrestle with this. Okay, and then come back and check out how to finish this question and understand or apply your idea of forces. Okay, first things first, torque. Where did that come from? Torque is basically the force times distance. Either force times perpendicular distance or perpendicular force times distance. The little thing like that basically means perpendicular. So two ways to calculate torque. So we need to know force. Force produced by what? Oh, electric field, right. So this P here means positive. So I'm going to, let's use a red color. Positive charge is here. Negative charge is here. So what is the force experienced by these two different charges that come together and form a molecule? Do you know what molecules are dipoles, by the way? Think about it in chemistry. Anyway, I'll leave that to you. Positive, negative charges. Okay, so we have an electric field. You can see the arrow is going to the right, which means if you want to think of positive, negative plates, left is positive, right is negative. So, whoa, this is very informative. Firstly, let's look at the positive charge. It's going to experience a force this way. Same direction as the electric field. Then the other negative charge will be opposite to that. So, this way. Different force. So think of it as there's a bar connecting these two and you're exerting a force like that. So something like, I cannot find my bar that I used to have. Like a pencil, and I'm pulling it like this. Whoosh. So it's going to rotate, or aka it's going to generate a torque. Now there are many ways to calculate this. You can either use this formula or this formula, depending on which one you're more comfortable with. I'm going to go with this one. I'll find the perpendicular distance and find the torque. One more shortcut you should know. This is actually a torque of a couple. What is couple again? Good revision. The magnitude of the charge is the same. So they will have the same force. This Fe is the same magnitude as this, but in different direction. That's what we call a couple. Same force acting to rotate something. So the shortcut to calculate the torque of a couple is one of the forces times the distance between both forces. How do I write this up? Perpendicular distance between forces. Okay, so if I extend the lines a little bit, I need to find what is this distance between the forces. I'll just call this D. Let's just not put the perpendicular there. So that's the D I want to find in this case. Because in that way, I don't have to choose, where should I choose as the pivot point? Here or here or here? Never mind. Shortcut a bit. Sort of couple, you can use this. So, you should do some trigonometry. How shall I do my trigonometry here to find the torque? Well, let me choose this triangle. You see a little triangle there? I'll try to draw it out. There we go. I'm going to redraw it as well so we can see it clearer. So this triangle is what we can use to find the distance here, because we know this one is 30 degrees. We know the distance between the molecule that gets given to us, 2.8 times 10 to the negative 10 meters. Very small. That's up here, given to us. And we can find D because of trigo. Yay. So let's find the torque. So the force is the same at both sides. 10 negative. What did I write? Force. That's not the force. Force is QE times D. That's better. For charge is 1.6 times 10 negative 90. Electric field strength given to us 5 times 10 to the 4. And lastly, the distance. Oh no, no more space. What is this distance D? Well, opposite hypotenuse. So that will be 2.8 times 10 to the negative 10 sine 30. A bit crowded there. Now let's put in all our calculations together. Many moments later, pressing calculators, you should get a torque of about 1.12 times 10 to the negative 24 Newton meter. Wow. Okay, many steps to this question. It hasn't appeared in a very long time, I think, because this is from 2010. The recent one focus more on different things of charge moving, but just in case you ever see a dipole, this is how you want to think of it. It's just two charges tied together by a rope, by a rod that holds both charges together, but that's pretty much it. And they can apply it to torque, chapter 5, because now there's two forces causing this little thing to spin and align with the electric field. So that's all for this section on electric fields. And that's all for today about field strength and forces. The next video is kind of like a sub-video to help us think about applications of these two ideas, force and electric field strength, called work done, energy, and potential difference. Okay, so that's all for today. I'll see you in the next video.